Have you ever built something with Lego bricks? You start with nothing and add one brick at a time until you have a cool creation. Now imagine doing that with metal, on a super tiny scale. This is additive manufacturing. Instead of carving a metal block down, waste, we build parts up, layer by layer. That lets us make shapes once impossible to make. Complex, lightweight airplane parts, custom medical implants that fit perfectly. Like a magic wand turning digital designs into solid metal. This technology is changing how we make things. For centuries, metal was shaped by heating, hammering, pouring into molds. Additive manufacturing breaks those rules. It uses a powerful laser or an electron beam to melt extremely fine metal powder layer by layer. Think of it like drawing with super hot glue, but it's titanium or steel. Each layer fuses to the one below, building a 3D part with precision. When you look at a normal piece of metal under a powerful microscope, you see something that looks a bit like a jumble of different-sized rocks packed together. These rocks are called grains. They are crystals of metal that grow as the hot, liquid metal cools down slowly. The size and arrangement of these grains determine a lot about the metal's properties, like how strong or bendy it is. In most metals made the old-fashioned way, these grains are fairly large and arranged in a random pattern. This structure has worked for a long time, but it's not always the strongest or most efficient design that nature can offer. Now let's look at metal that has been 3D printed. When we zoom in with a microscope, we see something completely different and amazing. Instead of those jumbled rocks, we often find a beautiful, repeating pattern of tiny, interconnected cells. These are called cellular microstructures. They look a lot like a honeycomb. They look a lot like the cells you'd see in a plant leaf. Each cell is incredibly small, often much smaller than a single human hair. This organized, cellular network is a direct result of the unique way the metal is heated and cooled during the 3D printing process. It's a structure that is far more ordered and intricate than the random grains in cast metal. The difference between these two structures is like the difference between a pile of loose stones and a carefully built brick wall. The pile of stones is okay, but the brick wall, with its interlocking pattern, is much stronger and more stable. So, how do these amazing little cellular structures actually form? It all comes down to a very specific recipe of extreme heat and super fast cooling. Let's walk through it step by step. The 3D printing process starts with a very thin layer of metal powder spread across a platform. A high-energy laser, guided by a computer, zips across the powder, melting it in a specific pattern. The spot where the laser hits becomes incredibly hot, creating a tiny pool of molten metal. This pool is like a microscopic cauldron reaching temperatures hotter than volcanic lava, but only for a fraction of a second. As the laser moves on to the next spot, the tiny molten pool it just created starts to cool down immediately, and it cools down fast. In fact, it cools hundreds of times faster or even thousands of times faster than metal cooling in a traditional mold. This rapid cooling is the secret ingredient. The metal atoms don't have enough time to arrange themselves into the large, chunky grains we see in regular metals. Instead, they are essentially frozen in place very quickly. This process of rapid solidification is what forces the metal to form the unique and organized cellular patterns that we've been talking about. The 3D printing process does something similar with metal. While these cellular microstructures are incredibly promising, making them perfect every time is a big challenge for scientists and engineers. One of the main hurdles is control. The 3D printing process has many variables: laser power, scanning speed, powder size, the temperature of the build chamber. A tiny change in any of these can alter the size and shape of the cellular structures, and that changes the final properties of the metal part. We are still learning how to fine-tune this complex recipe to consistently create the ideal microstructure for a specific application: jet engine turbine blade, delicate medical screw. Another challenge is ensuring these structures are stable under real-world conditions. How do these tiny cells behave when heated and cooled many times, like in an airplane engine? Do they stay small and strong, or do they grow and weaken over time? We need to be absolutely sure these parts remain reliable and safe for their entire service life. Despite these challenges, the future is incredibly bright. As our understanding grows, we are moving closer to designer materials. Imagine telling a computer, "I need a material as strong as steel, as light as aluminum, that resists very high temperatures." The real revolution is just beginning.